12.5 Exponential Models. In the last two lessons, we learned how to solve differential equations by separation of variables. One of the most important applications is exponential models. So here's an example. At t equals 0, one person infected with COVID-19 moved to a small town. After some time, this person spreads COVID to 2 other people. And then after some time, each of these 2 people spreads it to 2 more people. After some time, each of these 2 people spreads it to, yeah. And we're assuming that this person gets better over time. Write an equation that helps us describe the number of people with COVID-19, n, as a function of time elapsed, t. Okay. Now we're told that every person spreads it to 2 people. What that means is that the rate of growth of n is proportional to n, because the more people there are, the faster COVID spreads. That means that dn over dt, the rate of growth of n, is equal to k, our constant, times n. We learned this in 12.2. Okay. Now we use separation of variables. Multiply both sides by dt. Divide both sides by n. When we do that, we get, on the left-hand side, just dn over n. That's the same as 1 over n dn is equal to k dt. Okay. Now all the n's are on one side, all the t's on the other. We can integrate both sides. What is the integral of dn over n? Well, remember that the integral of 1 over x dx is equal to ln x. And of course, that's just equal to dx over x. Okay. So this integral gets us ln of n. Of course, n is always positive, so I don't even need the absolute value. It's equal to kt plus c. Okay. Next, I take the the exponent e to the power of both sides. So e to the power ln n is equal to e to the power of kt plus c. So properties of exponents, e to the kt plus c is the same as e to the kt times e to the c. But e to the c is just another constant, so I'm going to call that c, because e to the c is any number, so e to the c is just a number. So I'm going to call this c. E to the ln of n is just n, so we end up with n equals c e kt. Okay. So we have an exponential function. N equals c times e to the kt. Now what is c? Well, when t equals 0, e to the 0 power is 1, then n equals c. That means that c equals n when t equals 0 at the beginning. So we'll just call c equals n sub 0. That means the start number for n. Okay. That means that we have our equation n is equal to n naught. N naught means n0, the starting number for n, e times kt. Okay. Usually we use r for k, I mean, k could be any variable. So here's our exponential model. N is equal to n naught times e to the rt power. When t equals 0, n naught is equal to n. R is the rate of growth or decay. Let's plug this into decimals to see what it looks like. N equals n naught times e to the rt. I'm going to use x because decimals is using x. N naught is just our start number. So our start number we can find right here on this line when t equals 0. When n naught increases, the start number increases. When n naught decreases, the start number decreases. Okay. Next, r is how quickly it's growing. The bigger the r, the faster it grows. The smaller the r, the slower it grows. When the r is negative, it starts decaying. So when r is negative, we have exponential decay like this. And when r is positive, we have exponential growth. Okay. So here we have exponential growth. So this is our exponential growth model. When r is positive, we get growth. When r is negative, we get decay. So real life application, growth of COVID-19 infection. According to data from Johns Hopkins University, the number of reported cases of COVID-19 in the United States was as follows. So I have this real data. This is the number of people with COVID in the US. That was in January of 2019. Let's use decimals to find the best fit value for R. We know it's exponential growth, so it must look like this, n equals n naught e to the rx. I've already graphed our data. Here are real life points. As we can see, it is growing. It looks like exponential. Let's create our function. This n equals n naught. What is n equals n naught times e to the rx. I'm going to use x instead of r. What is n naught? Well, n naught is a start number, which is 279. 278. So that's always going to be 278. Okay. Now, exponential growth can have many different r's. We got to figure out what r is. Let's figure out which one's the closest. So 0.2 is too small. When r is 0.3 is closer, 0.31, 0.32, 0.33. Ooh, that looks really close. 0.34, that's too much. So it looks like r equals 0.33 is probably the best fit for the real life data. So that tells us that the best function looks something like n equals 278 times e to the 0.33t. Okay, where the start number is t of 0, this is t equals 1, January 22nd t equals 2, and so forth. Now we can use this function, 278 times e to the 0.33t, to predict how many cases there are on the next day. Well, the n equals 278 times e to the 0.33 times on January 27th, that's 7 days after, so t is 7. So that's it. So we're looking for 278 times e to the 0.33 times 7 power. Let's plug this into Google. We get about 2801. So I'm expecting about 2,801 people to have COVID-19. As it turns out in real life, the number is 2794. That's very close. So the exponential model is very accurate in terms of predicting the growth of COVID-19 earlier on this year in 2020. Sorry, this is 2020, not 2019. Okay. So yeah, the data really does look like this. The next year is 2794. So we have, yeah. Excuse me. I do not have COVID-19. I tested negative. All right. So that's an example of why the exponential model is really useful. And we got it from solving this differential equation. dn over dt equals kn or rn. Next example. The amount of money in a bank account, A, compounds continuously. This means that we continuously collect interest. So the rate of growth of A is proportional to RA, where R is the interest rate. If the rate is 2% per year, how much time will it take for the amount of money in the account to double? Okay, double means 2 times, triple means 3 times, and so forth. Half means divide by 2. So that means that dA over dt equals 0.02a. We can solve it the same way. Separation of variables, dA over a equals 0.02 dt. Integrate both sides. When we do that, we get ln of a. Again, a is positive, so I can ignore the absolute value. Is 0.02t. Again, we take e to the exponent of what we have. E to the ln a is just a. Oops. E to the ln a is a. Don't forget the plus c. Remember that e to the 0.02t plus c is the same thing as e to the 0.0t times e to the c. Okay. And that whole thing is just c. We can call that a constant, because e to the c is still a constant. So a equals c times e to the 0.02t. Okay. Once again, when t equals 0, e to the 0.02t equals 1, so a equals c. So we can just say that c equals t naught, t to the 0 power, not t sub 0, where t naught is just equal to t when so when t equals 0, a equals c. So we can say that c equals a naught, where a naught is equal to a when t equals 0. Okay. That means that we have our function, and it looks like a equals a naught e 0.0t. Okay. Now we want to find the t when a doubles. Doubles means 2 times. That means that a over a naught is equal to 2. But a over a naught is just equal to e to the 0.02t. Okay. I can take ln of both sides, take the natural log of both sides. When I do that, I end up with 2 equals 0.02t. Okay. Just be careful, it's not 2, it's ln of 2. That means to solve this, we can take e of both sides. E to the power ln 2 equals e to the 0.02t. Sorry, we don't have to do that. That's a mistake. We're looking for t, so we divide both sides by 0.02. So that means that t is equal to ln 2 divided by 0.02. Plug that into a calculator. ln 2 divided by 0.02. I get 34.66. So it takes about 35 years for the amount of money to double if the interest rate is 2%. Okay. Once again, I have neater notes written out here for you. Okay. Final example, exponential decay. Decay means to go down. So exponential growth looks like what we've seen earlier. It looks like this. Exponential decay actually looks like this. It goes down quickly and then slower and slower. Here's the example. Cobalt-60 decays with a half-life of 5.26 years. This means that if we have some cobalt-60, only half will remain after 5.26 years. So half, yep. We write an equation that describes the exponential decay of n, the amount of cobalt-60 over time. Okay. So half means n over n naught, the amount now divided by the amount we start with, is equal to 1/2, or 0.5. That means 0.5 n over n naught is equal to e to the rt. T is 5.26. That's how many years. And we want to know what r is when it doubles. So we have ln 0.5 is equal to r times 5.26. That means that r must be ln of 0.5 divided by 5.26. Plug this in a calculator. ln of 0.5 divided by 5.26. And we get about negative 0.13. It's negative because our function is decaying. Okay. So what did we learn? We learned the exponential model. N is equal to n naught e to the rt power. N naught is the start number. If r is positive, we have exponential growth. If r is negative, we have exponential decay. Doubling means 2 times. Half-life means the time it takes to get 1/2 for n over n naught to equal 1/2. Okay, that's it.